So welcome to SREcon, and thank you for taking the time to listen to some cranky old-timers talk about hardware and why their job is difficult. I'm John Looney.
I'm Panos Christeas.
We're both from Crusoe AI. We're one of the neoclouds that have sprung up in the last few years, focusing on AI hardware. All of the neoclouds, they have to have some reason that with 1 or 2% of the staffing and engineering resources of a big cloud that they can actually compete. So our edge really is that we're vertically integrated. And so we have this beautiful slide that shows down the bottom, we think about power, usually sustainable, low carbon for Crusoe. But yeah, that's one of our big things is we can find huge amounts of zero or low carbon energy. Then on top of that, we build our own data centers. We have a bunch of factories that build data center components and the likes, so we can build data centers faster than anyone else. Then on top of that, we have an AI cloud platform. The important bits of GPUs by the hour or managed Kubernetes, that kind of thing that you'd expect from any cloud. And then on top of that, I suppose, what people would actually like to buy. Like, no one really wants to buy a data center. They're a pain in the ass, right? You want to buy managed inference, managed training, and the likes. So yeah, that's like where we are. And we're going to talk mostly around the middle layers of the stack today. So the AI industry as a whole, though, is massively complex, right? Up the top, we have the cloud. We have those REST APIs, command line tools, pointy-clicky interfaces, et cetera, to your inference or training workloads. Below that, you're going to have something like orchestration, where you're going to put VMs, where you're going to put containers. Maybe you'll be buying bare metal, rarely. Underneath that, you've got drivers and communication libraries. These days, they're heavily influenced by the vendors. So you've got Rocky, you've got CUDA, NCCL, all of these kind of things that are vendor specific, and then a bunch of vendor or multi-vendor tooling like PyTorch. Underneath that, you're going to have your more common infrastructure layers, your kernel, operating system, any container runtimes. You've got virtualization tooling, the likes. We're going to talk a lot about that today. Underneath that is fleet management. So if you've got any number of machines, you're no longer going to have engineers running around the floor with USB keys, installing them by hand. You're going to need more than people walking through the data centers looking for red lights to spot bad hardware, which unfortunately we still need occasionally, but you're not going to depend on that. And that depends in turn on good DC facilities. Modern HPC systems, high performance computing, AI systems, they're not like normal servers, right? They're not as tolerant of dust or as tolerant of bad air, the thermal envelope can be a lot more brutal, so you can't be giving them, oh, today you get 3 degrees, tomorrow you get 20 degrees type stuff. No, these machines definitely need better environmentals. And they need a huge amount more power as well.
And we're moving into liquid cooling as well.
Oh yeah, actually there's a good point. So I was at the OCP conference actually with Panos about 6 months ago, and half of the vendors were showing their liquid cooling technology. Like, these things are changing rapidly. And of course, old school data centers cannot handle either the power density or liquid cooling requirements. I'm going to take a quick aside because that is important. In the old days, you used to buy square foot in a data center. They didn't care about your power. They didn't care about anything else because they assumed your servers were only so big and you could only fit so many into a rack. There were some entertaining things when someone would decide, really, you pay per square foot? We'll build a 50U rack and put as many servers as we can and drive you out of business. But also, they changed over to you now pay per power. When in a previous life, we were watching our data centers retrofitted as AI facilities, they tended to put a single rack of AI hardware every 10 racks, and then the other 9 were empty. That's because of the power density these facilities had. So the ones that Crusoe builds these days are 20, 30 times more power dense than the old days. You can get, our new factory in what they call an AI factory that we're building for Oracle in Abilene in Texas. It's 1.2 gigawatts in only a few dozen acres, which is kind of insane. And lastly, down here, energy sources. So this is going to be, do you build your own wind farms? Do you find geothermal facilities that are already exploited and build your facility there? One of the interesting things that's happening is concentration. So someone will build a big wind farm because, it's nice and windy. Then the grid turns around and goes, actually, that wind farm's really big. We're going to take maybe 5 years to hook you up to the grid. The wind farm kind of freaks out. They've already built a few $100 million of turbines, and now they have no one to use the power. So a big data center company will come in and go, hey, we'll move into your area. This sounds good. And so the data center moves in, and they have their phase one. They're soaking up all the power, and then they go, any chance you could build another 1,000 windmills? And then other data centers move in, and then other wind farm generators move into the same area, and then other people come in going, yeah, we got solar here as well. Other people go, oh, we got giant gas generators, and you end up with, I suppose, an energy park is the new phrase for it. The Irish government is looking at this model, for instance, and they're looking to put, I think, we'll see if it works out, but like 27 gigawatts of wind energy on the west coast of Ireland offshore, and hopefully then attract energy-intensive industries there. So this is going to be the future, but not the subject of our talk. Okay, so let's start with an old, well, I looked it up. It's only 2012 when people started saying, treat your servers like cattle, not pets. And pets alludes to the old sysadmin affectation of giving all of their servers individual names. The names of the planets was a good one. But, you anthropomorphize your server sometimes. You give a name like Eric, right? You care if it's sick. You get a little emotional when 6 years down the line, you retire it and replace it with a new box that also has a name. Once CPU stopped getting faster in the 2000s, I think we saw people, instead of every year or two, they'd replace their server with something bigger, they started getting more and more machines. And then sharding those workloads over multiple machines became a cool thing, and then multiple machines had multiple cores. But building out that ecosystem was a real pain, right? People had to build new kernels, new compilers, new SDK, new human brains were needed to understand how you split a mail server into 20 pieces. I was really proud the first time my machine installer could handle 10,000 machines being powered on at once. And that was like the, woohoo, we have finally worked out how to scale a machine installer stack, for instance, without DHCP falling over 10 times, or the database that backed everything falling over many times. Machines by then were getting serial numbers, right? They were like sheep. They didn't have names. And of course, out in the field, a sheep's value is 100 euro or something like that. It's not going to be a huge amount of money. So if it walks off into the distance and is never seen again, you're not going to miss one sheep because you've got thousands of them. And like any other rough sheep farmer, if one of these cattle isn't behaving itself, it gets replaced. Now, in a previous life, if a machine didn't work properly, we would have a look at it and go, can't work out what's wrong. It's definitely not healthy. We'll just dump this into the lemon pool. And over time, the lemon pool ended up being hundreds and then thousands of machines. None of them were worth the time repairing them. I remember one day getting really angry and said, there's like 2,000 machines in the lemon pool. I'm going to pick one at random and debug it. And I spent 3 days at it and was like, yes, I found out how to detect when a machine is kernel panicking on multiple cores concurrently. And that's definitely a CPU problem and not a memory problem, because all of the cores are on the same CPU die. And of course, there was 3 other machines that had the problem, and it took me 3 days. And it was like, hey, I've saved the company 1,000 euro with 3 days' work. This is not terribly productive. Right, this is an amazing AI-generated image of a modern GPU server. I just love how it would go on fire immediately if plugged in. Yeah, don't use LLMs for designing electronics, please. Just checking. Okay, so what are in these big, beefy boxes that we have these days, right? There's going to be a pair of the world's biggest CPUs. And I remember thinking, hold on, you've got all this GPU hardware. Why are you spending 20,000 on CPUs? Well, you have to get a massive amount of data in and out of GPU memory. And you can completely saturate the biggest CPUs you can get. You can completely saturate them just doing memory transfers in and out of off the network, et cetera. Yes, it would be great if everyone did kernel bypass. We're not there yet. You've got a massive amount of memory, 32 $5,000 DIMMs. The motherboard is not cheap, but not incredibly strange. It's got a huge amount of PCI on it. We've got the big GPUs. I went looking. The B200s are pretty good GPUs that you can buy discreetly, and they're about $45,000 a piece. You've got your network, no big deal. NVMe, no big deal. And then this last one down here, this $118,000 expansion card for hooking your GPUs together. And, oh, sorry. That whole machine is about $700,000, the same price as a very expensive Texas Longhorn steer that you're going to use for breeding others. Now, this is not a $100 sheep. If this guy scratches himself on barbed wire, he's going to get cosmetic surgery, probably better cosmetic surgery than you can afford, right? The farmer absolutely not only knows this cow's name or steer's name, but it knows the names of all its parents and grandparents. And this is much closer to the analogy that we're looking for with HPC hardware. So let's keep talking about expensive pets, right? The most expensive horses today are descended from old Arabian racehorses. And hundreds, thousands of years of selective breeding to get the fastest animal that loves to run fast with a human on its back. They can cost millions, right? It can take 4 years to see the result of a breeding experiment with one of these. And model training, to an extent, is a race too. It can take maybe not 4 years, but it'll certainly take an extensive amount of time for you to take a model, make some changes, run it through the experiment framework, and then decide, yeah, this is better or worse than the previous iteration. And model building, training, it breeds the best models through a series of experiments, and the faster you can iterate, the higher the quality of the model at the end. So the company that can sustainably, repeatedly train models quickly wins the quality race and therefore the market. So, right, we want to do we want to go for the racehorse then, the one machine that's faster than everything else? Well, maybe not, right? Think of the craze of yesteryear. They were lightning fast in a specific direction, right? Utterly crazy. You look at it the wrong way and it'll stop working on you. It'll get sick if you feed it the wrong data. I'm not sure if a cray could bite you, but I'm sure it would if it could. And the days of those super giant vector-based machines are long gone. Cray went out of business in 1993. They bet against, well, smaller ones. These are Connemara ponies descended from old medieval war horses of the Middle Ages, tiny war horses that were meant to go across soft ground and bogs with unarmored people on them. But yeah, these ponies, their ancestors never saw a road. They could run for miles across rough ground and bogs and never break a leg or anything. They survived harsh winters and never saw food supplements like you'd feed a modern racehorse. So I like to think of these as the servers that replaced the giant craze. And like a medieval army, though, in AI training, you can't start your next stage of training until the last one finishes. So you need reliability. You can't have a load of racehorses and half them break their legs on rough ground the first time goes, right? Racehorses make crappy war horses. Like that, low-quality machines make really bad AI training systems. Don't know if anyone's old enough here to remember the Beowulf clusters of the 1990s, when people were like, I can just take all these old PCs, hook them together up into an MPI cluster and distribute computing amongst them. And it's awesome. It's going to replace all these HPC systems that we're doing weather modeling, et cetera, with. It turns out they worked quite well for some scenarios. In fact, the modern hyperscalers have fleets of millions of these small, individually, not quite reliable, not quite redundant, not quite super performant machines, and they make incredibly powerful clusters from them. So I would describe it as we've become experts in making reliable clusters from unreliable, smaller components. But yeah, that's not going to work for us, right? Model trainings are billions of transforms over trillions of parcels of data, and then distributed to every core in every GPU in every node of the cluster. And each transform can't start until the previous transform completes, and that data from that transform is over every part of the cluster. So we need ridiculously low latency networking, because you can imagine you run your compute, every node is now finished, Or actually worse than that, the last node that finishes, then you can start distributing all of the data. And until all of that data, all the results from the previous run are done, you cannot start the next one. And so what we see in the real world is about, with the world's best networking that you can afford, about a third of the time, maybe at best a quarter, but usually around a third of the time that a cluster is running, it's actually waiting for data. So your GPUs are only running at full speed on average, 2/3 of the time. If you used commodity Ethernet, like the old Beowulf clusters, you'd probably be at 5 or 10%. It would be completely pointless. The machines are far too fast for that network. So let's talk about this bad boy, right? Irish draft horse. Its ancestors were a mix of the Connemara ponies and the ridiculously large war horses that came in with the Spanish Armada in the 1500s. Not as fast as a racehorse, but it's big enough to jump anything. It's not as tame either. It'll throw you off if you act the maggot and then look back guiltily at you and say kind of sorry. But it'll set you back between 40,000 and 300,000 euro for a good one. So these things are, somewhere in the middle of those cheap ass ponies and the seriously expensive racehorses. But really reliable, damn strong, can do anything. Realistically, when we're trying to make machines for AI clusters, we can't go full-on redundancy, right? You can't put RAID in everything. You can't do the old Stratus continuum trick of lockstep CPUs, like 4 CPUs to implement one to make it super reliable. You can't do RAID on the RAM or anything like that. So you just need high-quality machines. But if you're going to have hundreds of them, thousands of them, you can't have them individually over-reliable, or you end up wasting a huge amount of money. So a single link on one of these clusters going slow slows down everything. Because remember I said you can't start the next run until the data from all of the previous computations have completed. And so each one of those runs, it might take 10 microseconds, it might take 20 milliseconds. It's not going to take a lot of time. But if every 10 microseconds, you're going to have one link throwing errors, so your retries are adding 5, 10, 20 microseconds onto that 5 microsecond run, yeah, your whole cluster could be half speed, quarter speed very, very quickly. So we need fast and we need reliable. And worse yet, as we increase the size of a cluster, the cost of having a reliability problem goes up. So the best we can hope for, and this is horrendous, is that we build a somewhat reliable cluster out of very reliable components. Okay, another amazing hallucination here. Trying to explain the logical diagram, like what drives these big machines and what kind of problems do we end up with. So we need super low latency networking, right? InfiniBand is the top of the line for this. On that old, hot and crazy scale, it's definitely all the way up. InfiniBand has, is it 2 microsecond latency versus Ethernet might be 5 to 10, depending on what you're doing with it. Rocky is one of the newer technologies where they're adding InfiniBand features to InfiniBand and driving down the cost of this low net. Yeah, sorry, yes, that's why I suppose. It also supported RDMA, which is why Rocky is RDMA over converged Ethernet, and I suppose remote data memory access over converged Ethernet was a bit more of a mouthful, so they just go with Rocky. So these modern servers, you can see, actually it's not linked it terribly well, but each NVMe drive is linked to a GPU. That's because for performance reasons, you want to be writing your checkpoints directly to each dedicated NVMe card. If you go over 2,000 nodes with the biggest switches you can buy today, like 64-port switches, you can only go to about 2,000 nodes, and then if you want to go over 2,000, you need a third layer. And that's great. You might double your performance, but your latency goes up. And if you're going from 2 microseconds to 4 microseconds, oh, congratulations, you've just halved the amount of, you've doubled the latency on your whole cluster by trying to grow it too big. So there's an element of you're better off building a bunch of models at around that kind of 2,000 GPU stage and merging them together later, or swallowing it and going really, really big and just say, we'll lose a bunch of that or tolerate that extra latency and just scale up hugely. But you're back to, if you have 10,000 nodes, 20,000 nodes, 50,000 nodes, and one of those goes and everything slows down, that's a problem, right? So we do need to make a difference between how fast we can go and how reliable it needs to be. PCIe, there's a lot of PCIe lanes on these machines. It's a great workhorse. PCIe 5 is witchcraft. Shouldn't work. No one should do a bus at 16 gigahertz, I'm just saying, especially not lots of them. And a bus like that at 16 gigahertz, if you run it over any kind of a distance, you're going to get, you're going to need retimers. So you can imagine if you have PCIe coming out from a CPU going down the motherboard, a link often over wired cables, which freaks people out, to the HGX that has all of your GPUs on it. You're going to have retimers on both sides. They use power. They have their own firmware, their own complexity. They can also break. Yeah, the NICs that we talk about here, some of them are going to be for the fabric, so the GPUs are directly connected to those, and they're going to use that for talking to each other. On the front end, most data centers these days, they're heavy SDN based, so the smart NICs are evolving into full computers in their own right. I think one of the ones I've seen recently had 32 ARM cores and 16 gigs of RAM, like on a NIC. It's kind of insane. But more opportunities for interesting things to happen. We tend to go for the most recent expensive top-of-the-line optics. 400 gig is, well, actually, yeah, 400 gig is pretty good. 800 gig is out now. The way optics work is kind of scary. Every time they do a double in, when they double in frequency, technically you're going to get a quadrupling of the amount of heat generated from the optic. So it's not unusual for old optics to be maybe 8 watts at this stage. It's 800 gig, and your new latest greatest 800 gig optics might be 24 watts. So if you have a 64 port switch with all of that, my arithmetic is not good, but that's kind of like a kilowatt or kilowatt and a half heater in front of your switch. So even air cooling for switches is running out of road. And we think for the 1.6 gig optics coming in soon, they're just going to have liquid cooling. So you're going to have a little pipe of water running around the optic units in the front of each switch.
That's not 1.6 gigs, that's 1.6 tera.
Oh, sorry, 1.6 terabit
We're
optics.
into the tera territory.
Yeah, wow. Oh my God. Networks shouldn't be that fast. Now, oh yes, the power usage does quadruple, but of course, we then try and make transistors smaller, etc., and they will drop, so it's not completely linear, but those cutting edge optics are always using way more heat. And it's hard to dissipate. If you don't dissipate it quickly, you do degrade optics over time, so they do start failing. Yeah. And lastly, the GPUs have enormous amounts of memory. Like some of these big 200 node clusters could end up with a petabyte of RAM between system memory and GPU memory, which is a lot of opportunities for failure as well. Cool. So, would you like to take over for a while and tell people about all of the ways things can fail?
We explained a little bit about how the hardware now is so exotic, so crazy, but that brings failures, right? That cannot be as reliable, as simple to make right as the previous generations. So we can start talking about networking, the possible failure scenarios about networking, cabling, optics, NICs, drivers, control plane software, and SDN, because we're not longer on a plane network. NICs are getting smarter and doing more than ever before. We tend to want to chase the cutting edge. But that needs engineering capacity to report the dozens of bugs you find on the vendors before you ship. This can be a direct conflict with the desire to get hardware in front of customers as soon as possible. We can run bonded interfaces on the front end, that's okay. Even if it drops to half speed, the front end network is not an issue. We rarely max out the bandwidth there. But optics modules don't last forever. That plays a role. When a new standard comes out, the old, as John said, tend to use much more energy, and then even the electronics shrink. But this is about, like, as John said, like in the order of 24 to 28 watts per optic, and that means a lot of energy, a lot of heat dissipated there, and failure modes, mechanical and electronic failure modes. Now SDN, we need SDN, especially when we have like tenants, customers there, and that is tricky. If you try just to do SDN on a CPU, that takes a lot of CPU capacity and also drives a lot of I/O in there. That's why we use the smart NICs that can do all that offloading for us, but have their failure modes on their own, right? The CPU can just lock up and you spend days debugging why the CPU, although it can ping the network, will not pass the traffic around, right?
And one of the common failures can be we're not in control of what customers want to do. So if a customer wants to create hundreds of pods talking to their hundreds of VMs, there's no other way of doing that other than tell every node, hey, set up all of these hundreds and thousands.
So there is a balance of like allowing our customers to do what they need, give them the security that their network is isolated from other customers, although on the same fabric, and keeping that very, very efficient against the hardware, right? Well, kernels are not bulletproof. These machines do strange things with virtualization. We virtualize something to pass it to the customers. We virtualize the network. We virtualize the GPUs. We virtualize the NVMEs, the block storage, the backend storage we pass to the customers. And all that needs to pass through the kernel, but in a very, very efficient way, which means we're using the most exotic features of the kernel, and we're causing the most exotic bugs in these features because they're very, very rarely used only by a handful of companies that work on this model. Then, along with that, we're working on like a moving target, which is the versions of the kernel, the versions of the firmware that we have underneath. So every time we try to solve or optimize a feature, there is a new firmware or a new kernel feature, and we need to make sure that this works along in tandem with anything else. Like we need to pin all versions, deploy the complete cluster, tests, apply the workloads as close as to reality as possible, and then find the new wave of bugs that we need to resolve and do yet another cycle. Like we talked about training cycles, we have our deployment cycles that we need to test all this stack.
I was thinking of a recent issue we had where deploying a new platform, again, cutting edge, and we contact the vendor and say, hey, we've found bugs in how we virtualize the CPU in your platform. And they said, sure, no problem. You need to be running this branch of this kernel. And we were like, oh, okay. And then a while later, a separate team is trying to make sure they're saying, hey, network performance isn't particularly good. And they said, you need to be running this kernel, this branch, this with this patch. Or the network card doesn't work. And we're like, what? And then in parallel, somebody else trying to virtualize GPUs was saying, hey, we're running into bugs like this. And they said, yes, that's only supported in this kernel. And we're like, we're buying this hardware from you. Can you get all of your kernel teams to talk and come up with one kernel version that works for all of these? And they were like, oh, no one's asked us that before. And that helped us realize, oh, we're literally the first people who are getting this out the door. And we're teaching our vendor how to actually finish their product. But that kind of collaborative approach is definitely the only way that we can do it.
We need the full stack of features. We cannot live with one feature missing there, right? So we talked about these SREs, these very, very expensive network adapters that talk InfiniBand or Rocky. And they have similar problems to the front-end network cards. And there is more of that, because they need to talk directly to the GPUs. Like they could fall over. Some fabric managers that control the traffic flow into these InfiniBand networks also cannot tolerate a NIC failure or cannot tolerate a different version of firmware on these NICs. And if that happens, then the whole backend network degrades so much that training speed goes into orders of magnitude worse.
And actually, I was just thinking there, a fabric manager is, I suppose, the HCA version of spanning tree protocol. So you have your full mesh set up, but it turns out you can handle many different types of network failure. If a switch dies or a link dies, you can, instead of going out through your network link, you can actually route over the GPU to GPU bus. So it's almost like the network card will send, or your network packet goes through a different GPU and out through a different port. All very cool, all very fancy, many more opportunities for failure and bugs.
We're a bit like sort of dying. So yeah, another failure mode is the optics themselves. Like we're talking about fiber optic networks that cannot tolerate bit error rates like traditional Ethernet. They're not built for unreliable optics. So a little bit, a glitch or a thermal throttling on this 6 micrometer fiber can make your network much worse, so we need to repair it immediately. Going to sweep. So surprisingly, the GPUs themselves have not been that bad for us. So they have 200 billion transistors, but they're quite reliable, and their monitoring architecture helps a lot in that. But we have a lot of problems with interconnections, like the way that the GPU modules is placed on the XGX board, or the interconnection of the XGX board to the CPUs and whatnot. These things fail. They're mechanical, a little like. Given all the power that goes through any thermal expansion, something can introduce an electrical misconduct, and we need to fix that. So yes, like even the amount of thermal paste, the application of thermal paste, because these things dissipate so much power, matters, and that manifests itself into an AI model training failure, or your whole cluster being incapacitated. So at the same time, everybody wants to have the latest GPUs because of their efficiency, and they're not surprising that they ship to eager customers before the firmware and software ecosystem is fully baked in. One of the firmware's most important jobs is to paper over like any deficiencies in the silicon. There is hundreds of processors that need firmware. Every piece of that may have a bug or so, and we tend to find these bugs very, very soon after release, as soon as a cluster is deployed, and we need to put some customer workload in it. And some of that can only be triggered once you get the real customers with the real workloads, like the previous speech here, like all this full stack deployment, and you find bugs that the vendor could not have found, like by doing traditional testing. So there is, like, it's not adhered for new release framework. So a new framework stresses the GPU in ways that could not have been done before. Let's say when DeepSeek was introduced versus the previous LLMs, it introduced, like, it triggered bugs in the hardware that we wouldn't have seen.
And right? Worse than that, everyone downloaded the DeepSeek models that day they were released. And so we were seeing lots and lots of customers with bugs around the same time. It was like, what the hell's going on here? Do we have some crazy fleet problem? And then someone said, oh, no, these are running DeepSeek. I was like, okay.
Yeah. And even more so, like the way that the power ramps up from an idle GPU that is under 100 watts to 1 kilowatt per die in the GPUs, all these things, like even the power sequence, can stress the hardware and the software and the firmware in such ways that we could not have predicted. And now we have a problem to solve, and we need to solve it very, very fast for our customers. So we cannot afford to have a full, development cycle to go back into the silicon and fix it, right? Of course, the traditional problems of computing do still apply, like just more so. Bigger thermal gradients, more opportunities for hardware to fail. Any small deviation from this optimal state that we want makes the hardware unreliable, can crash our AI models, and can hamper the jobs, right? We rely, as said before, we rely on the CPUs to do very, very intensive I/O, because it needs to transfer so much data from the network, from the storage into the model, into the HBM of the GPU memory. and so on. We talked about PCIe 5 numbers, like the amount of throughput there is amazing, and we need that to go without a glitch. So a marginal defect means you can have a failure, or the best case is a serious degradation that will halt your model and make it slower.
Yeah, it's not unusual for it to fall back to half or quarter speed. And again, that means your whole cluster goes back to half or quarter speed because a single PCI link or a single DIMM is throwing a load of correctable errors. Like, they are correctable, but it does slow down the transfer.
Yeah. So how do we go about it, and how do we make that a success? Like, this is an engineering problem for us to solve. So let's say GPU disappears during the training. What can we do? Can we carry on? Can we page? So unfortunately, we cannot just carry on. Like, this is a sharded model. It all goes in parallel. So if one node fails, if one GPU fails, the whole parallel model is paused in the best of the cases until we can get a replacement, replace that, and restore the cluster to its full size, right? We cannot run with lesser of the original size of the clusters that the model was supposed to run on. So you need to have a replacement machine. In the 90s, as John said, you could have multiple machines waiting over to take some load, but now, given the numbers we said about the price of each machine, that's not longer a viable option. Like, it would cost us, the cluster operator, it would cost us like double or quadruple.
Yeah, and actually, so in a normal cloud world, you expect, my machine's broken, please give me a replacement immediately, and your vendor will have that. If you're buying AI hardware on the cloud, often what they'll do is they'll say, oh, you've bought 64 machines, no problem. We'll actually charge you for 72, and we'll keep 7 or 8 aside here for spares, and off you go. And as they fail, they swap them in and out for you. One of the options we do is we can say, we can totally do that, or we'll just give you 72, and you self-manage your spares. And of course, all of our customers go, oh yes, please. That means normally I'm running much, much faster. And then of course, one falls over, and they go, oh, I'm sad. But at least if they're, have a decent infrastructure internally, they can go at option C here, immediately eject the broken machine, reshard, and start running again slightly slower.
So we can talk about checkpointing. That's a specific procedure when we're doing training models. So there is millions or thousands of cycles of training inside the training of one model. So what we can do is copy the data over to some non-volatile disk NVMe, so that the training of the model can resume if one node fails. Like, give us the ability to pause the model. But if you think about the numbers there, that like if we get the optimal checkpoint rate as twice CT, the time between checkpoints, divided by lambda, the time of 2 checkpoints square rooted, we can come up with a number that like it sounds like a month, but is like 10 minutes every 1 hours. It's okay. But if we have so many nodes, that means having a 10-minute penalty every 10 minutes. And that now becomes a problem, like it's not even possible by numbers.
And you say, how long does it take to checkpoint? It actually depends on how many machines you have, because modern GPUs might have 100 gigs of RAM in each one, so you might end up having to write most of that to a persistent data store. So, yeah. Go on.
So I'll just go on. So we can use the traditional bathtub curve to look for components that would have problems. So there is heavy failures in the first days or weeks of the machines running, and then quite normal failure rate, and then as it ages, you have a large failure rate again. So we do run burn-in tests to detect that initial failure rate. But at the same time, we don't want to keep machines always in a testing mode. We need to pass them on to our customers. So we need to find that sweet spot, which is like 1 hour of testing for a new machine would do. So also, like I can say of anecdotal story that we were running these machines for so long, and then we decided to do a maintenance cycle and pass the latest firmware and software, and then we realized that after doing the software and rerunning the burn test, we had a 20% failure rate. Like 20% machines that we would not confidently pass to our customers because we needed to debug them, check if a power cycle would bring them back, or we needed to replace a component or reset something to fix them. So,
but these were all machines that had been working, our customers thought were working perfectly well. But when we took them out and ran through burn-in, we found marginal problems. Maybe it was a DIMMs throwing a lot of ECC errors. Maybe it was an NVMe drive that was half speed. Maybe it was a GPU that was thermally throttled when it shouldn't be. But these are all problems where, like any car, you should probably send it in for maintenance regularly because the mechanics are going to find problems that you don't know yourself.
So I think we can skip that.
I was going to say there's one interesting bit here, though. We will then hand over to customers we then do benchmarking. And benchmarking is you run a massive workload that really stresses the GPUs and run it for multiple hours, maybe even a day or two, to see long-tail latency, long-tail reliability problems. Like is there a GPU that's going to fail after 6 or 8 hours? Worse yet, can you find network links maybe that after 3 or 4 hours of runtime, they drop to 90% or 80% of the full capacity of the link? We will then often bring in external teams. There was a blog post we wrote recently with the PyTorch team where they ran their new version with FP8 and FP4 to see how it performed on the latest generation of hardware. And they ran for about 26 hours without seeing a failure, and then they saw a failure, we swapped it out, it was fine. But I remember they said to us afterwards, 26 hours, that's like absolute best in industry. And I was like, how is a machine running for 26 hours best in industry? And then I thought about it and was like, well, that's like 2,000 GPUs, 4,000 InfiniBand cables, 8,000 sets of optics, 500 CPUs, 32,000 DIMMs, all working perfectly for 26 hours. And it's like, actually, that's pretty cool.
We need to measure that. We need to use all the existing technologies like BMC with Redfish, because we need to be out of band and collect metrics while the customer is running. We can supply a local agent for the customer to run in this virtualized environment so that they collect their own metrics and report it to us so that we know what's not behaving well. And then we can feed that to the traditional Victoria metrics or like voluntary and the host side telemetry that we are collecting to find, but then we need to do all this data exercise to synthesize it and spot the anomalies. Like it's machines that are straight out broken, that we know that they will not run, but there is also the machines that are marginally about to fail, and we need to detect them and we need to take them out on the next cycle so that we don't deliver them back to a customer and have them complain about.
In the last talk, I thought it was very interesting that half of all people running these training jobs don't have monitoring. And it was like, no, this explains so much that we can take machines back after 6 months and go, loads of these are broken. And like there was one cluster I took back and it had 5 bad InfiniBand links. And it was like, you guys must have seen some problem here. But again, only because we did the burn-in, we were able to find them and hoosh them back out.
Yeah. And then we go into this regular maintenance that's like firmware update solves a lot of problem, fixes all these teething issues that have with brand new hardware that we're receiving. And like we need to have detection, and then we need to narrow down this maintenance window to give the machine as fast as possible back to the customer with fully coordinated maintenance and doing enough of scale of testing to tell that the machine is healthy or not, and weed out the ones that are not behaving.
Cool.
So I think we're over time.
Yeah. We can do this quickly. So some recommendations if you do find yourselves running large training or inference workloads. Definitely assume nodes are going to fail, right? Build automation to eject them and notify your vendor and request repairs. You have to have a checkpointing plan. Please do this early rather than when you realize you're going to need it. And then protect the model and any artifacts. Assume that do not store them on ephemeral storage, please. And then lastly, just like any vehicle, request downtime for firmware and kernel updates. Thanks very much.